An ideal amplifier has an infinite gain, an infinite input resistance, and it should have almost zero output resistance. So, in the 5 transistor OTA, we are trying to find the difference between the input voltages V1 and V2, and the output voltage is the amplified version of the difference between V1 and V2. So, to have the highest gain, the topology that we can choose is common source amplifier. If I am giving input V1, I'm taking the output here, let's call this RD. So this topology amplifies V1. But like, what if I want to amplify the difference between V1 and V2? Here, V out is equal to ID into RD, and ID is GM times VGS. VGS here is V1. Now, if I want to find the difference between V1 and V2, what can I do? I can give V2 at the source terminal. Now, the output equation becomes something like this: GM V1 minus V2 into RD. However, we know that for an ideal amplifier, the input impedance needs to be really high. So let's see the input impedance in this case. The impedance looking into the gate terminal is infinite, but the impedance looking into the source terminal is 1 by GM. So this will not perform as a good amplifier. What can we do to increase the input impedance towards the source terminal? Now, we can add a V2 through a voltage buffer to increase the impedance. And we know that a source follower acts as a voltage buffer. So let's use the source follower topology along with this common source. So V1 goes here, and I'm going to add the same RD for uniformity and symmetry. So I give V2 here, and I take the output out of the source terminal and connect it to this source. And now this gives rise to the classic 5 transistor amplifier. We call this a 5 transistor OTA because this resistor, this resistor, and the current source can all be realized by a transistor. So let me draw this a little bit clearer. And we give the second voltage there. Now output is taken from here. What do you think the voltage here is equal to? The small signal voltage here. Let's find out. So, in order to find the small signal voltage here, I can reduce this circuit into something like this. So there's RD connected in a common source structure, And we know this is a symmetric circuit, and the impedance looking into the source terminal is 1 by GM. So I can reduce this into 1 by GM, and the output is taken out of the source terminal. And what do you think this represents? This is a classic common drain structure, because the input is given at the gate and the output is taken out of the source terminal. To make it simpler, first I'm going to consider it without RO, and V out by V in without RO for a common drain structure is GM RS divided by 1 plus GM RS. I think these are the formulas that it's better to have it in your mind. These simple formulas, it just makes things quicker. And here RS is 1 by GM, and V1 is V out is V in. I'm sorry, V in is V1. So V out can be given as GM into 1 by GM into 1 by GM into V1. V out is equal to V1 divided by 2. Since this is a symmetrical circuit, we can say that Vx is equal to V1 divided by 2 plus V2 divided by 2, and this is called the common source voltage. Now let's find the small signal current ID. ID is given by GMVGS, and we know that if we take one half of the circuit, the gate voltage is V1 and the source voltage is V1 plus V2 divided by 2. So the small signal current ID is equal to GM times V1 minus V2 divided by 2. Because obviously here, since the current source is open circuited in small signal, and the VDD would be grounded, would be AC ground. The input voltage to a differential amplifier has two components, and it can be given as something like VIC minus of VID by 2. So VIC is the common mode voltage and VID is the differential voltage. And when we are analyzing the behavior of the circuit, we see what happens when we feed only the common mode voltage, and we also analyze what happens to the circuit or if we feed only the differential voltage. Common mode voltage is given by V1 plus V2 divided by 2, and the differential mode voltage is given by V1 minus V2 divided by 2. When I give a differential signal at the input of an amplifier, um, what do you think happens at Vx? What would be the voltage at Vx? Since this circuit is actually symmetrical and linear, um, when two linear systems are put together, and the voltage in between the two systems would be equal and opposite due to superposition. So Vx here is equal to 0 volts, because the voltage at Vx due to V1 would be some linear term times VID by 2, and the voltage at Vx due to V2 would be a linear term times minus VID by 2. So essentially Vx would be 0. Now I can reduce this circuit. If I'm considering only the right half of the circuit, I can write it something like RD V out is taken out of here minus VID divided by 2. VDD is grounded, is an AC ground. This is a small signal model, and this is grounded too. Now we can easily find V out. The small signal V out is this RD, GMRD minus VID divided by 2. And if I'm including the effect of R naught with R naught, it's simply GMRD parallel with R naught minus VID by 2. And obviously there's a minus, and if I expand minus VID by 2, we get GM RD parallel to R naught V1 minus V2 divided by 2. And this is called differential mode half circuit. Now if we take the other component, the common source component, and I am giving the input as VIC in both the terminals, we know the gate voltage is same, the circuit is symmetrical, so the voltage seen at the drain in both the terminals are same. So it's basically a short, and I can now reduce this circuit into something like this. Now I can basically reduce this circuit into something like this. Both the RDs are parallel, so this would be RD by 2 the output is taken here, VIC, and if this is called I naught. Now what do you think the small signal voltage at V out would be? Well, the small signal voltage at V out is 0 because the current source at the source I naught sets the voltage in the circuit. So any changes in the gate voltage is not going to change ID. So that's why the V out is 0. So the total voltage considering both the components would be something like VIC plus VID divided by 2, which is equal to 0 plus hence the output voltage would be the sum of both the common source response and the differential response, and the common source response is 0 volt and the differential response is equal to GM RD parallel to R naught V1 minus V2. And this half circuit is called the common mode half circuit. Now I can realize this circuit to a 5 transistor OTA. I can replace the resistors with a transistor. The resistors will be replaced by a PMOS, and an output will be taken here. And the small signal output voltage V out for this circuit, with considering R naught, would be GM, and the total resistor seen at this point. So these two resistors, so it would be R naught P parallel to R naught N into V1 minus V2 divided by 2. This is V1 and this is V2. And this is the classic 5 transistor OTA. And thank you so much for watching, and stay tuned for more videos. Bye.